So now we will start with the next chapter, that is design of compression members. Now the design of compression members would be very different as compared to the design of tension members. First of all, what is a compression member? A compression member is a straight structural element which is subjected to two equal and opposite compressive forces. Okay. Now, what would be the ideal case? The ideal case would be that the member is perfectly straight. The load is applied at the center of gravity of the cross section, due to which we can assume that the entire cross section will be subjected to uniform stresses. There is no initial curvature or crookedness present inside the member, as well as there is no residual stresses. If all these conditions exist, then we can say we are dealing with the ideal compression member. But unfortunately, this particular condition is not available in reality. In the reality, what the member that we will be getting will not be perfectly straight. It will be having some initial curvature present inside it. Due to this initial curvature, when we will be applying the compressive load, this curvature will go on increasing. And there will be a stage, and there will come a stage when the curvature of the particular element will be so large that you cannot apply any further load. It will become, you can say, failed by the lateral buckling. So this is what the problem in case of the compression members, that although we have the philosophies for the ideal case, but here we have to design a real column which will not be having some, you can say, particular straight segment. It will be having some curvature present inside it. In addition to this, there will be some residual stresses. There may be chances of local buckling failures. So all these factors actually reduce the strength of the column. Okay, so first what we're gonna do in this particular chapter is, first we will learn the theory for the ideal column, that if we have an ideal column, what would be its strength. Then we will announce a reduction factor which will take care for the all these imperfections that actually exist. So when we will multiply this imperfection factor over the, you can say, the ideal strength column, it will result into the strength of the actual column. Okay, now generally the columns on the basis of their failure criteria can be divided into three categories. One of them is a long column, short column, or you can say the intermediate column. They are all relative to each other, and you can tell that which particular column comes under which category based upon its slenderness ratio value. Now what is this slenderness ratio? That is nothing but ratio of effective length to the radius of gyration. Now what is this effective length? Effective length is the length which depends upon the end support conditions and the unsupported length of the column. So all these factors we have to learn in this particular chapter. So first we'll see some introduction, then we'll be moving on to the types of compression member, then we'll discuss the effective length, slenderness ratio, what type of sections can be used as a compression member, and then we'll finally learn how to find out the strength of a particular compression member. Okay, so let us start with the introductory part. Introduction. So what is a compression member? A compression member is a straight structural element, okay, which is subjected to two compressive forces at its end. Two compressive forces at its end. All right. For example, let us say we are having a vertical member like this. This is a vertical member, and this is the centroidal axis, or you can say the longitudinal axis of this element. Now the next question is, where will be the load acting? Generally we assume that the load will be acting at the CG of the cross section. So you can show that here we have the loading just passing from the longitudinal axis, and the support will also produce a reaction in this upward direction like this. So you can say eccentricity is what? 0. There is no gap between the loading as well as the CG of the member, due to which at a particular cross section, what you can say is that the amount of stresses generated would be equal at every fiber. So what you can write down is that everywhere the stress generated would be equal. So this is the case of, you can say, ideal scenario, that every fiber is subjected to equal stresses. So what do we have? Uniform stress distribution. As you know, if there is some eccentricity, if there is some eccentricity, there will be, in addition to the loading, there will be some bending effect also. Now, because of that bending moment, one side would be bending compression, one side would be bending tension. In that case, you cannot say you will be getting the uniform stress diagram. So, for an ideal case, or you can say as per the definition, we can say that a compression member is the one which is subjected to two equal compressive forces passing from its, you can say, the longitudinal axis, or you can say the centroidal axis. Okay, what are the other scenarios that we can consider? That the column should be perfectly straight. Okay, that this body is completely straight. We can write down this particular member is perfectly straight. Perfectly straight. As well as this particular member is not having any kind of residual stresses inside it. I have told you, when we manufacture the structural steel, the process it goes through, there will be a lot of temperature changes and there will be a lot of pressure applied over it. So even before the actual loading, there will be some residual stresses present inside the member. Although for the ideal scenario, we do not say that there are some residual stresses. So this is the main concern over here, that as per the definition of ideal column, whatever the conditions are required, we do not get them in the reality. So we can write down this point. An ideal compression member is the one. An ideal compression member is the one which is. So what are the credentials for an ideal compression member? First credential is it should be perfectly straight, which is perfectly straight. That means, in other words, you can say it should not have any initial curvature present inside it. It should not have no initial curvature present inside it. Okay. Second, you want the stress distribution to be perfectly uniform across the section. For that, load should be totally non-eccentric. Load is non-eccentric. Load is non-eccentric means eccentricity should be equal to how much? 0. There should be no eccentricity. Next, there will be stresses only because of the loading. No initial stresses should be present. That means no residual stresses. No residual stresses, as well as there should be no type of imperfection. No imperfections. It should be perfect. No imperfection or crookedness. Okay, so these are all the, you can say, credentials to be called as an ideal compression member. Whatever the theory that you might have dealt with, like Euler's theory, where you have taken several assumptions that load is non-eccentric, you can say the material is homogeneous, isotropic, no initial stresses. So that Euler theory that you have already discussed in the strength of material, it is only valid when we have a ideal compression case. But now the problem is, in the case of steel structure, we know that we won't be getting a perfectly straight member. Of course, there can be some eccentricity due to which there will be some bending effects. Yes, there are some residual stresses present inside the member, and yes, there can be some imperfection also depending upon what shape it has been manufactured. So in a note we can write down, practically above conditions never exist. All right, practically all of the above conditions that we have listed never exist. So we never get a ideal compression case. So what case do we get? We get a case like this. The member that we get is having some curvature present inside it already, somewhat like this. You can say somewhat like this we get the member. I have shown to a very large scale, but it cannot be seen by the naked eye. But yes, there will be some, you can say, deviation. There will be some deviation in the curvature. Somewhat like this. Okay. So for example, this is the initial curvature present inside the member. What is this? This is already the initial bow type curvature. This is initial bow curvature, which is already present inside the member. Okay, even before the loading, this member is not perfectly straight. And now, even though you apply the load at the center of gravity, even when you apply the loading at the center of gravity like this, you apply the loading. Okay, these are the reactions and the loading. So what is the line of action of forces? The line of action of forces, you can draw it straight away like this. This is the line of action of forces. You can say like this. Okay, this is the line of action of forces. And where is the centroidal axis for this member? The centroidal axis for this member will be passing from this side. It will be passing from the member like this. All right, so due to this, what you can observe is that there will be a particular cross section where the centroidal axis would be maximum deviated from the line of action of loading, due to which you are getting a large eccentricity. There is some eccentricity because of this curvature, like this. There is some eccentricity, delta you can say, which is already present, and let the load is P. Now because of this particular member, in addition to the compressive load, is also subjected to a moment. There will be a moment generated equals to how much? M is equal to P into delta. So a moment would be generated like this. You can say a moment will be generated. M equals to P dot into delta. Now this moment will lead to more increase in the curvature. There will be more increase in the curvature. When the curvature will increase, there will be more increase in the delta value, and again the moment will go on increasing. There will be a stage when the deflection will be so high that the moment is generating at a very high rate as compared to the axial compression. Basically, you cannot increase the load any further because the deviation is so large. This is what we call as the instability of the column, or you can say buckling failure of the column. So there will be a stage when you can say this particular deviation will be so large. This particular deviation will be so large that it cannot increase any further. It cannot increase any further value of load. So once it becomes a very large, you can say the lateral deflection, we can say that the column has been failed by the lateral buckling. Understood? So this is nothing but the lateral buckling in compression members, which is the main reason for instability. Okay. Why do we do not have this kind of problem in case of tension members? Because even if there is some curvature present inside the member and you apply the tensile loading, the member will tend to straighten out. It will become straight. So in tension members, even if there is some initial curvature was present, we are not taking it as a limit state. But here, because of this deviation which is already present inside the member, upon loading, the curvature will increase. Due to this increase in this curvature, bending moment would be generated. As the bending moment generated, again more curvature will come, which will again increase the lateral deflection. So there will be a stage that will come that no load can be increased any further. Only the bending is very, you can say, high generated. So at this particular point, the curvature would be at its maximum, you can say, and the load value cannot be increased further. So at this particular point, you'll say that the column has failed due to the lateral buckling, or it is, you can say it as main instability reason for the failure of the column. Okay, so you can write down this point. Generally, initial curvature is present inside the compression elements. Due to which when the member is loaded with load P, with load equal to P, okay, in addition to the compression, bending effect is also generated. In addition to compression, bending moment is also generated. Bending moment is also generated is also generated. How much bending moment is generated? P into delta, where delta is the initial curvature present. Okay, so this is bending moment generated. Now as you will increase the loading, the moment value will increase, due to which the deflection value will increase. As the loading increases, as the loading increases gradually, the lateral deflection delta, the lateral deflection will also increase, which will increase bending moment, acting on the member. Okay, there will be a stage, there comes a stage when the lateral deflection is so large, is very large, due to which most of the column strength will be, exhausted in resisting the bending only. Now the deflection is so large that the upcoming bending moment is taking majority of the strength of the column section. That is why you are not able to increase any axial compression. So the lateral deflection is very large, due to which bending moment is increasing, at a greater rate as compared to axial compression, So basically you can say that most of the column is right now sustaining the bending only instead of the axial compression. So what we can say, the column has already failed under the buckling. This is known as, or you can say this instability in the column is known as, lateral buckling, Understood? So what is the problem in our particular, steel structural members? That they have some initial curvature present inside them, and there are some residual stresses also, due to which when we are applying the load, it is actually not deforming in the direction of the load. The member is deforming perpendicular to the direction of loading, or you can say it is moving laterally outward. This lateral movement of outwardness of the column is resulting into its failure, which is called as the lateral buckling failure. Now depending upon the failure, there can be three types of, compression members, or three types of columns. It can be a long column, it can be a short column, or intermediate column. All of them depends upon their respective value of slenderness ratio. But before this, I would like to tell you all that there are some other types of compression members also.